let's look at the variation of the mean temperature with X for the second boundary condition, which is the constant temperature. So here we are looking at the Tm as a function of X for constant wall temperature, tube wall temperature. From the energy balance, what we get, the variation of Tm as a partial differential equation for showing the variation of Tm as a function of X was P over m dot Cp H Ts minus Tm. Now here, if I do a little rearrangement here and knowing that Ts is constant, so dTm over Ts minus Tm would be pH over m dot Cp times dx. And if I take the integral of this one from the inlet Tmi to Tmo, and here from 0 to L, then the integral of the first term and replacing that one is going to be the log of Ts minus Tmo, Ts minus Tmi here in the system. Or, you know, I can make it to any location. So I'm just going to replace this one with respect to the x. So this would be the integral of that. It's going to be equal to minus p x m dot cp. And I'm just going to make it h average along the length of the pipe. So let's say this is the pipe that we are looking, and this is x direction from 0 to L. Here is Tmi, here is Tmo, and H is the average heat transfer coefficient. And does not change for the H does not change for the fully developed region, but it changes with the interior region. Now, if I rewrite this equation, it's going to be Ts minus Tm function of x, Ts minus Tm and I going to be exponential of minus p h average m dot Cp x. Now, if I make a plot similar to the previous case, so let's say I have this tube 0 to L. This is x, and this is T. The wall temperature is constant, so I'm just going to plot that as a constant. This is Ts. Everywhere is Ts here. And the fluid temperature, the mean fluid temperature starting from Tm and I, is going to exponentially increase till you're reaching to Tm and O. So the difference between them, delta T, is Ts minus Tm, and it's going to be a function of x. And so to evaluate the rate of heat transfer, we are going to find out like what we can put. So like, let's say for the length of this tube, we are going to find out how much heat has been transferred. So the Q convection for the overall length of the tube is going to be m dot Cp Tm and O minus Tm and I. Okay, I can write it based on the delta T. If I define delta T as a Ts minus Tm, so this could be m dot Cp Ts minus Tmi plus minus TS minus TMO. I'm just adding and subtracting TS in the right hand side. So it's gonna be m dot CP delta T I minus delta TO. That's one of them. And from here I can get the m dot CP. So m dot CP is gonna be Q convection divided by delta Ti minus delta To. And I know from the top part, I know these relationships. If I bring it here, it's gonna be log of Ts minus Tm and O. I'm just writing for the whole length of tube. Ts minus Tm and I is gonna be minus P. Instead of X, I'm gonna replace it with L because I'm writing Tm and O at the outlet. M dot Cp times H average. Now this is gonna be natural log of delta To divided by delta Ti. And for the right hand side, I'm gonna have minus PL H average. And instead of M dot Cp, I'm gonna replace its equivalent here in this equation. So we're gonna have Q convection, and here we're gonna see delta To minus delta Ti. So I can now rearrange this one to get Q convection that happens along the whole length of the tube. Is gonna be HPL delta To minus delta Ti divided by natural log of delta To divided by delta Ti. I guess I made a mistake. This is Ti To, so this is gonna be positive here. This is the surface area P times L, so it's gonna be H SAS surface area delta To minus delta Ti divided by natural log of delta To divided by delta Ti. So this is going to be the Q convection. And what I'm going to do, I'm going to call this one. So this is a sort of like if you consider this pipe, what happens here is this is TS is L, and we said for the fluid temperature, the mean temperature of fluid is gonna change like that from Tm and I and Tm and O. So in order to find out the total Q that is exchanged between the fluid and wall, I need to get this delta T at any of these X location. Now, this is the way that we have done it. So that Q convection is going to be H average along the surface of the wall. So this is AS, and we have H average that we have evaluated for the internal surface. And this is going to be showing the average of that delta T that we require. And that's what we are going to call LMTD or delta TM. So we are calling that one delta TLM or LMTD, and showing that as a delta To minus delta Ti natural log of delta To over delta Ti. And we are going to call that log mean temperature difference. And this provides this LMTD. Let me just write it down here. supervise and average difference between Ts minus Tm, which is a function of x. So in fact, what we are doing here is, instead of having all these changes, we are replacing that for the sake of evaluation of the overall heat transfer. And we are getting this LMTD as an average temperature difference that happens along the length of the pipe.